so ionisation. What are we doing when we make an ion? What's happening with
Gaining or losing electrons?
gaining or losing electrons? That's right. But specifically, when we're talking about the ionisation energy of an element, we're only going to be losing electrons. And just like we talked about our electron energies last time, how the last added electron will have the highest energy, and last in is first out. That last electron is going to be the easiest to remove because it's at the highest energy level. So it's not as close to the nucleus. It's going to be easier to remove. And if we look at any element, if we add energy, enough energy, what we can do is remove an electron. So what we're talking about here is not a chemical reaction. What we're talking about is a physical change or removal, okay, by adding energy. So just like we added our energy with our flame tests, we excited those electrons. If you add even more energy, you can give the electron enough energy to leave. So of course, magnesium doesn't react this way, does it? Magnesium will react by losing 2 electrons, by donating 2 electrons. But we can ionize magnesium and have it only lose 1 electron. And in actual fact, you can see in our books, that it would have to be 733 kilojoules per mole. So if I have a mole of magnesium, then I need to add 733 kilojoules to electrolyze. This is also a gas, not a solid. So we're talking about ionizing the element vapor. So that's a lot of energy. We've already had to make the magnesium gaseous, and now we're adding even more energy to remove that electron. Now, if we add even more energy, then we can continue to remove electrons. And we can do this until we have removed all of the electrons. Okay? So there's 2 kinds of questions that we need to be able to answer. And that is when we look at the trends of first ionization energies. So what do you think that means? What does that sentence mean? The trend of what?
How much energy is required to remove that first electron, or the one furthest from the nucleus?
Yeah, so we're going to be looking at a number of elements, and we're only taking 1 electron. And what we're comparing is the energy. And that is what is in that table on page 26. If we look here, it's got the ionisation energy for the first 20 elements. First ionisation energy. So we can tell it's the first ionisation energy because it tells us it's E1. And it's been quoted there in kilojoules per mole. Now, if you look at that, it's quite a variety of values. And it doesn't start small and just get bigger. It starts sort of in the middle, gets smaller, gets bigger, gets smaller, gets bigger. And you can see the graph of this trend down the bottom of the page. Okay, so if we're just going to, the other thing that we then often look at, if we're not looking at the trends, is we look at the successive ionisation energies for an element. So that's another kind of question that we will encounter. Sometimes we can have a question that involves combination of the two. But for this one then, what we are doing is taking away every electron or a lot of electrons from the one atom. So we then would have E1, E2, E3, E4, say, E5, E6, each, like the carbon. We're going to say, well, what are the successive ionisation energies as we remove successive electrons from that carbon atom until it's got none left? So they're the kinds of questions that we need to be able to answer. Now, I want you to look a bit more closely at the graph on the bottom of page 26. And what do you notice? Which elements of those ones that are graphed there, the first 20, have the lowest ionisation energies?
Group 1 metals.
The group 1 metals. Why do you think they are going to have the lowest first ionisation energy?
Because there's one electron in each cell.
Yep, they only have one. When they lose that one, what do they gain?
Noble gas.
Noble gas stability, and so they are going to then basically, we think about our electron configurations now, where we know that full, empty and half-filled have special stability. They lose an electron and their remaining subshells are all full. They're filled to that principal quantum number. Now if we look a little bit more closely at lithium, sodium and potassium's numerical value, which one is the lowest? Can we rank them?
Potassium's the lowest.
Potassium's the lowest. Which one's the middle? Sodium. And lithium is higher. Is that what we would anticipate? Because the one we're removing for potassium, we've got distance and shielding, so that means that it was going to take less energy to remove. Which elements have the greatest first ionisation energy?
The noble gases.
The noble gases, does that make sense?
Yes, because they're already at the full stability, the full noble gas stability. So they really don't want to lose any electrons.
They don't, and so it's hard to remove them. We've got that trend again of it being hardest to remove from helium, then a bit harder, a bit not quite as hard for neon, and then bit easier again after that for argon. Does that make sense?
Yeah.
Again, because we've got what? Greater distance and shielding from the nucleus. Okay, so we're looking at we've bookended it. We've looked at the lowest and the highest. But you will probably notice that it's not a straight line trend between them. It goes up and it drops down a little bit, and it goes up and it drops down a little bit. Why is that happening? So if we look at the lithium value, and we see there for beryllium, it's a bit harder. That makes sense, doesn't it? Why should it be a bit harder to take one electron from beryllium?
Is it getting closer to the
No, remember, if we're here, we've actually filled.
Oh, the S
We've filled 2s2, haven't we? It's full. So it's harder to remove because it's got a full subshell and it's stable. So, but then we get to boron, and it requires less energy to. Why is that going to make sense?
Because it's only one
We're removing the one from the P shell, but
Yeah, so it's only got one P. So it's going to be, if we take away the 1p, then we come back and we've got a full 2s, haven't we? Sorry, when I say the 1p, I meant one electron in the 2p. Or, yeah, just want to make sure that you're clear what I mean. Okay, so we get to boron, and then we get to carbon, and it's sort of, our trend is looking reasonable again, isn't it? Nitrogen. Why do we drop down for oxygen?
just over the half full.
it's the first one where you've got 2 in one of the P subshells.
Yes,
Electron.
so oxygen it's going to be take relatively less energy because by losing that electron it has that half-filled stability. Okay, and then we head up back again to fluorine and then on to neon. And so the two dips we saw were boron and oxygen. Boron because it was the first electron in the next subshell, and oxygen because by losing that electron it was half filled. So if we look at the trend then for our next period, we see then that we go up for magnesium, we come down for aluminium, and we come down for sulfur. So the trend is continuing on, but you just do need to understand that we're looking for full, empty, or half-filled as being lower energy than, and so if you're losing an electron to get to that stage, then it's going to take less energy than it would otherwise. Okay. Now, if we now look at successive ionisation energies on page 27, the example here is beryllium. You can see that to take the first electron away from a beryllium atom requires 899 kilojoules. To take the second electron away from the beryllium ion, single positive charge, requires 1748 kilojoules. So 899, 1748. But to take the third electron away, 780, sorry, and then 2940. What do you notice about where is the big jump in energy?
Between 17 and 14.
Sorry?
Between 17 and 1700.
Yeah, so that's between the second and third ionisation energies. And that's the way we would normally describe it. So for beryllium, let's have another look at our periodic table. My first ionisation energy takes away the second S, 2s electron, doesn't it? The second ionisation energy takes away the first 2s electron. What happens then? What happens when we take the third electron away?
Gains the noble gas stability.
Yeah, we're taking it out of the next layer down. So the moment we do that, it takes a lot more energy. And then the fourth ionisation energy is taking away the last electron. So when we completely empty our principal quantum number energy level, we're going to see a huge step down to as we take out our inner electrons. What this means is that we can look at successive ionisation energies to determine the valency of an unknown element. Because I can look at that, and what am I going to say the valency is for this? 2. Okay, so I can see then that these must have been the valence electrons, and if this was an unknown element, I could say it would have a 2+ charge on its ion. Does that make sense? Because we're looking for the big jump. Now it's always going to increase. Why will we always increase?
Because you're moving an electron. It's closer to the middle.
We are always moving removing an electron. But why must it always increase? What can you tell me?
Because you're moving closer to the centre, so there's less.
Sorry?
You're moving closer to the centre. Like the shell you're taking away from.
You're always removing the least stable electron that has the least attachment to the atom.
Yeah.
The one that, essentially the least energy.
Just the size of the subshells.
Not really, no. No.
You're always going to remove one that's easiest to remove first.
You are. But if this now, if I add this much energy, I end up with that. What is the charge? What are these numbers here telling me? What it's telling me is the electron to proton ratio. And so the more electrons I remove, the harder it has to be to remove the remaining electrons, because we've got an ever-increasing charge differential. Okay, so we've got before here we've got the same number of protons and electrons. Now when we take away one electron, I've got 4 protons and 3 electrons. So those protons are very pull on those remaining electrons quite a lot. And then I take away another electron, and that charge differential is even greater. And so at this point here, I've got 4 protons and 2 electrons. So 4 can pull a lot harder on those 2 than the 2 remaining 6. So it's a bigger differential in the charge attractiveness, and so the nucleus is pulling very hard on these electrons always. So the moment that you take away an electron, it will always require more energy to take the next one. All right. If we look on the next page, page 28, table here of first ionisation, of successive ionisation energies. Again, trying to highlight for you that you can hopefully see where the big jump occurs. So if we look at sodium, do you agree that the big jump in energy is between the first and second ionisation energies? And if we look at magnesium, the big jump is between the second and third ionisation energies. And for aluminium, the big jump is between the third and fourth. And for silicon, the big jump is between the fourth and fifth. So we have to look to see where the really big jump occurs, because it's always going to get bigger. Now we can also look at, we'll worry about atomic radii another lesson, I think. What an important summary, if you like, is on page 29 about the trends for the period. So the ionisation energy increases across the period in general terms because we have a greater number of protons attracting those valence electrons, and so more energy is also needed to remove that valence electron. Ionisation energy decreases down the group because we've got the lower attraction, we've got an increasing distance and shielding. Okay, so that's just a reminder of what we're talking about. So now you've got some questions that you can do on page 30. Now anything that's to do with the periodic table trends, there'll be a few questions there that you can't do, but just skip over those ones. I'll write up the numbers of questions that you can do on the board.